right, good morning everybody. It's 10:20, so let's get started. Welcome back. We'll start off Module 4, Polymer Structures, with a lovely question on top hat here. So feel free to consult with your neighbors if you would like. But the question is, which of the following is true for the following weight distribution of polytetrafluoroethylene, or commonly known as PTFE or Teflon? So in your top hat app, you should be able to see this plot here of molecular weight distribution, and it gives you the fraction of polymer chains on the y-axis and molecular weight on the x-axis. So I'm going to make this a little bit smaller so that you can see your options, but you should also see your options on your screen on your device. So sometimes we do quantitative computations, as we've done in class, possibly on your exam, say, definitely in your homework. And some of the questions will also be qualitative like this. Okay. Yeah? That's up to you. Based on the homework submission, some of you have already finished your homework for the second homework. So presumably those that have submitted know how to answer this. Others of you are in the middle, so maybe the answer is no. And some of you have already submitted homework for the third homework that is already open, due in 2 weeks. So it's up to you. Okay, we're just about there. There's about 30 of you left to get your answers in. Feel free to talk with your neighbors. Consult, discuss, debate. Okay, we're just about there, so let's get started. Okay, let's look at your responses. Okay, so the majority of you says that from the data that's given here with the weight distribution of PTFE, a polymer, that you say that the average molecular weight is larger than the number average molecular weight. So clearly there's terminology in here that I don't know if you know, which is why I polled you to see if you read the chapter beforehand before coming here. And it might be that you read it, but you were unclear. So this also helps me gauge how much to go into detail for today's lecture. Because even though I posted lecture notes, I hope to take this opportunity to actually engage in somewhat of a dialogue with you, despite this being a lecture hall and despite your expectations that if you're in a lecture hall that you will be lectured at. So if you've taken the opportunity to read the chapter ahead of time, let's discuss it in greater detail. It's clear that the majority of you either have the intuition for the correct answer, or you've already read ahead, and this tells me quite a bit about what you've done over the weekend. Or you're just, you've done research in this area, and this is something you know left and right. So it tells me actually a lot to poll you before we introduce a concept. So I hope that explains why one would ask you about a subject matter that I haven't discussed before, okay? And since I've already told you what the correct answer is, you already know, but the majority of you is already there. So that's great. We're starting off on the right foot. Now, for those of you, because there is a significant number that, well, it's about 50%, so maybe that's not the most, glamorous number to talk about or to write home about, but there is a significant number of you that have said that the number average molecular weight is larger than the weight average molecular weight, and that is not true, so we'll talk about that. The average molecular weight, about the same amount, just a little less, says that the average is 45,000 grams per mole. So presumably you looked at the peak of the Gaussian distribution and said, yeah, it looks like something like there, or the log normal. And it looks like that could be the average. So you probably relied on some math skills that you've developed over the years and made an educated guess. That's not unreasonable, but that's not the definition, okay? And then some of you, still significant, it's not a minor contribution, said that the degree of polymerization cannot be determined from the distribution data. So either you guessed that or you legitimately thought that, but that is not true. We can determine, based on the data that you're given, the plot. It involves some computation, but you can calculate the degree of polymerization from this data that's given here. Okay? And the data is in plot form. It's not in a data table. So you would have to extract those numbers from a plot as you normally would if you were doing experiments, right? You tabulate the data from whatever it is that you're doing, okay, in your respective fields. So also not true, and we will go through an example on how to do that. And let's say we don't have time to go through the example. Well, fear not. Oops, sorry. Oh, let me end this for a moment. Fear not, because I've gone in great detail with this tutorial video that's been uploaded on how to calculate the number average and the weight average molecular weight given a distribution in plot form. The examples in your book gives you a data table and spits it out and says, here, this is it. Either way is fine. Obviously, you have experience reading a plot. We'll go over that. And if you're given a tabulated set of data, you should also be able to read that off. Okay? But when you're given a plot like that, weight distribution and the fraction, you should absolutely be able to compute these numbers and talk about polymers in this way. Well, now that we've gotten your blood going, let's actually discuss chapter 4 in your Callister textbook. Okay. Maybe today, maybe not. Okay. So there are quite a number of learning objectives. I leave this on here so as to guide you. I don't always go over every single learning objective, but the major points that we'll be talking about today, and you can go over this in great detail, is we're going to be talking about the structure of polymers and how that relates to properties that you care about. So if you're engineering the liner of a soda can or textile, right, polyester, or if you're making a device that's going to be a bio-implant, the polymer structure is what you care about because that dictates the properties, right? That dictates biostability, chemical stability, integration into whatever it is that you're making. So polymer structure is extremely critical to talk about properties. And then, of course, how do we control these polymers? How do we even make these polymers? Clearly, in the chemistry department, there are polymer scientists, polymer chemists who care about how to control the molecular weight, how to control the polydispersity. If you're telling me I need, for material selection, I need X with 50,000 grams per mole molecular weight, it is actually not trivial to give you exactly that with a tight distribution from a synthetic point of view. So there are people who worry about that day in, day out. We're going to focus more on the properties. We'll talk about the synthesis a little bit because that does give you some intuition as to why there's polydispersion in polymer materials. And that, of course, gives you polydispersity in your properties as well, like melting point, stiffness, things like that, okay? So they're all related, but obviously our focus is less on the synthesis, more on the properties. And then we'll talk about terminologies like weight average, number average molecular weights, what is an isomer, what is a stereoisomer, what's a cis-tran isomer, right? And what's a copolymer? It dictates all of your life and all of your electronic devices, by the way. So we'll talk about that in great detail, okay? So obviously, they're everywhere. You already told me this because you thought that polymers was, contributed the most CO2. So there's some tone that's affiliated with polymers and plastics. But really, it doesn't have to be. And there are biopolymers, there's biodegradable polymers, and we can absolutely recycle every single polymer that's out there, okay? I think the popular science approach is plastics is bad because it goes to the landfill or it goes to the middle of the vortex in the Pacific Ocean and we can't do anything about it. That's actually not true. It's an economics problem. We can do things about it, but it's like desalination. You can remove the salt from the ocean, so why isn't every coastline doing this? It's really expensive to do such things, and sometimes your yield is not worth recycling. Okay, economically, is it worth recycling in terms of our health and the future of this earth? Absolutely. But are you willing to pay the price for it? It comes down to that, okay? But polymers are everywhere, and they're not necessarily bad. And obviously, you find them everywhere. There are naturally occurring polymers. If our definition of a polymer is poly, there's many of something. Here in this case, it's a mer, so it's a repeat unit. So if there's many of repeat of something, technically, your DNA is a polymer. That's a biopolymer. Cellulose, repeating units of the C6 chains that you see here, that's technically a polymer as well by definition, right? You have a mer, you have a repeat unit, and that gets repeated. That's a polymer, fundamentally. Then, of course, this day and age, certainly, we wear polymers left and right. A lot of the clothes that we wear, textiles, they're synthetic blends of polymers and something, maybe something organic. But technically, polymers are also organic because by definition, things that are organic, as you remember from OChem, is that it has carbon. And there's carbon everywhere in the backbone of these polymers. So technically, polymers are also organic. And they also take place in, let's say, solid electrolytes for batteries to make them safer so that you don't have flammable liquid electrolytes, which separates your positive electrode and your negative electrode. And there's a lot of studies that are being done right now on how to do that, going from ceramic solid electrolytes to polymer solid electrolytes. So I don't think I have to tell you in great detail that polymers are everywhere and that you should care about them. But you could see here the structure of this biopolymer versus, of this polyester versus these block copolymers, and we'll talk about block copolymers. Clearly, they're quite different, right? So just the class of materials itself has a wide range of properties just based on the chemistry. So we touched upon this a little bit in regards to the carbon-carbon backbone. So we see here, this is a monomer, mono being one. So this is the starting unit. And then if you want to polymerize this into a polymer, you make the mer. And this can be done by radical polymerization. So here you can see that there's a double bond, right, where I circled in green. If you have any other radicals that are out there, and you can induce the radicals, you can introduce species like an acid. So let's say hydrochloric acid. The Cl will have a radical on it, and then that radical will attack that double bond, and now that can propagate and will link to another mer. So let's say it finds another mer, which has already been initiated, and then so on and so forth, right? So this can be a very fast reaction, and it can be done with a chemical catalyst. So you put in hydrochloric acid. It can be with a metal that can induce these radicals. So this is radical polymerization. You could also have just light polymerization. So that can also induce, so if you, some monomers, you just put them out, it's UV activated in the sunlight. Obviously, you can turn on a UV lamp. But you can also just put it out in the sun and you notice a chemical change. That is polymerization happening, okay? And so that can also induce free radicals, and thus you can have radical polymerization that way. So tons of ways to do it. And what eventually happens is you have these MERs that cross-link, and N is the degree of polymerization, or the DOP, or in your book, it's the DP. But either way, it's degree of polymerization. So how many repeat units do you have in your chain? That is absolutely critical for determining melting point. More repeat units, higher melting point, more bonds to break, okay? So we can talk about that, and we discuss it in terms of degree polymerization, and we discuss a polymer regarding its molecular weight, or the mass of a mole of chain. So you have a lot of chains. So when you have a mole of it, you describe it with molecular mass or molecular weight. Technically, molecular mass would be more accurate, but your book and the majority of the community also uses molecular weight, right? That's dependent on the gravity that you experience. So obviously, this would be different on Mars or on the moon or whatever. But in this particular case, it's interchangeable. Okay, so here is the outline of how one describes the characteristics of polymers, right? Certainly you have the chemistry. So what we saw before were 3 hydrogen atoms bonded to the backbone, carbon-carbon backbone, and then there's a chloride atom bonded to one of the carbons. So we change the chemistry. Let's say we take out the Cl and put in an F, right? Or what if we take out H and Cl and put in 4 Fs? Now you have tetrafluoroethylene, or PTFE, right? And so that's Teflon. That changes your properties dramatically just by changing the chemistry, not before you even get to the structure itself. And then when you get to the structure, you can see we describe it in a variety of ways. So here, these little dots are the MERs. So each one of these dots is a MER. So if we have ethylene, like this, right? These are the repeating units, and it's drawn this way, right? Sorry, not here yet, because I'm talking about the dot. So the dot looks like that. That's a MER. So they're all connected in a line. All the carbons are connected. Even though it looks floppy like this, because the carbon-carbon bond, it can rotate 109 degrees, 109.5 degrees. That's the rotational steric freedom that it has. It makes it look, so even though we call it linear, it makes it look floppy like this. And the longer your chain, you can imagine it starts looking like this and this, but still, right, it's still linear chain, because we're talking about the backbone, carbon-carbon backbone. Okay, so it can flop all at once, but it's still a linear chain. And then you can have branch. So let's say in this example here, I'll circle in red. So here's branch. So your chain could start going like this, and then it could start bonding this way or this way. That's a branch chain. And then let's say these two chains, still in red, these two chains make covalent bonds this way. We call that cross-linked. And then you can have more complicated covalent bonding between the MERs, and we call that networked. So you can imagine that linear chains we can pack more readily. Networked, we can't so much because it's quite bulky, the sterics. If you remember from OChem, right? It's quite steric. It's flopping around. So it has different dimensions. Yes, question in the back. Yeah, so the covalent chains, so the carbon-carbon bonds are covalent. Carbon-hydrogen, that's a covalent bond. And then there's also, you could have these chains, so you can have secondary bonding between these linear chains. So in the chain itself, you have covalent bonding. In between the chains, because it's hydrogen to hydrogen, you have secondary bonding. So it's weaker. And we talked about this when we were talking about secondary bonding and low melting point and temperature, relative to, let's say, something that has all, you know, metal bonding like nickel, copper, and whatever. But now we're just talking about amongst polymer chains. Yes, question? Okay. Okay. Thank you. I mentioned that because some of you in BME may have taken that. So that speaks to you. I give a lot of examples of MECI and structural materials, so I apologize for the minority when I speak to the majority. So I try to even it out. So if it speaks to you, great. If it doesn't, thank you for letting me know. I'm happy to go into greater detail if you have a specific question about that. Anything that I've said here, when I say organic chemistry, that means if you've taken it, this should be a breeze and it's a review for you. If you haven't taken it, listen up. But I don't test you on anything that was from OChem 101 unless I've explicitly stated it here and discussed in class. And I hope I've been clear and explicit about that since the beginning. What happens, oh, okay. Yeah, so you can have, let's say, carbon here, okay? Let's say it starts branching here. That's a covalent bond. So you can have something like this. So what you may have seen or not seen, I'll go over it. Most people don't write it like this because it's ridiculous and it takes a long time, as you can tell, based on how long it takes me to write all this out. So the representation and what you've seen in your book as well looks something like this, right? More representative of what you've seen in the previous slide. So that's sort of the representation here and here and here and here. So these are the MERs that are bonded together covalently. Mm-hmm. A MER is any one of those yellow dots. Correct. That's not guaranteed. That is absolutely correct. It doesn't have to be. So crosslink doesn't have to mean any sort of periodicity. Mm-hmm. Yeah. So I'm going to repeat the question in case you didn't hear it in the back. The question is there anything that dictates, and correct me if I'm wrong, is there anything that dictates the exact molecular weight or something that's predetermined or a priori if those of you who read the literature often, if you do research? No, not particularly. That's all dependent on your friends in organic chemistry that you can consult with, since some of you have not taken OChem. So that's a minor detail that I don't focus on because it is not the focus of this class, but thank you for the question. And yes, I'm not saying that people don't know what they're doing in life, okay? These are a new class of materials. It's not like, you know, polymers are running rampant in labs and we don't have control over them. We do absolutely do, but it's difficult and it's ongoing area of research for those who work on this area. Okay, so then we'll also talk about, let's say you have, right, we were talking about how you can connect a chloride ion, or let's say you bond a fluoride ion, or some bigger group. Like in your book, you've seen some phenyl groups, some other branch chains that are connected to the backbone. Whatever it may be, we can control the chemistry, and that how it's bonded dictates the isomeric states. So if you haven't come across the term isomer, it just means that the formula is the same, right? Let's say it's, well, there's an example that we'll go into. But let's say you have something like this, and let's say this is a Cl or something like that, right? Where it goes, where it's bonded matters when you polymerize this material. So here, to jog your memory, this means out of the page. This dash means into the page. It's to represent a 3D rendering on a 2D projection, okay? And so what we've seen before with the monomers, we see the double bond, right? That means it's unsaturated. And then when it becomes polymerized, all the bonds are single bonds, so it becomes saturated. Okay, and you can see examples here of methane, ethane, propane. Okay, different boiling point. So you could also see that the boiling point is increasing with the number of carbon atoms. Okay, that's telling you something about the number of bonds in the system. Okay. Okay. So you'll also come across things like normal butane. So this may go back to your question all the way in the back about the branching and the covalent bonds, right? So you could have something where all the carbon atoms are in a chain, linear chain like this, or with the same 4 carbons, you can have 3 in a chain, as you can see here, and then 1 branching off. That could also happen. Okay. So there are different ways of describing the same formula. As you can see here, there's 4 carbon, 10 hydrogen, 4 carbon, 10 hydrogen, right? Yes? Yes. So if this were, well, so you can have, this is just a chain so far. It depends. If we're calling this ethylene, if the monomer is ethylene, it would look something like this, in which case you would have 2 repeat units. So we would describe this as, oh, I mean, typically, one does not deal with butane as a polymer. When we're talking about polymers, we're talking about higher degrees of repeat unit, like many more than just 2. But could you technically have n equals 2 repeat units? Absolutely. But this is more of a molecule. We treat it as a molecule because it has different properties than that of something that's like C100H, corresponding hydrogens around. But the point of this is not so much to talk about the polymerization aspect, but this is more to talk about what to talk about isomerism and how do we describe the naming convention for a linear chain versus a branch chain. Okay, so hold that thought. I'll come back to that because we'll come back to isomerism. Okay. As engineers, you might care about how to rein in these properties. Okay? These materials, these polymers, have been around not as long as you think. Given how prevalent they are, you might think they've been around for a while. The field is relatively is mature, but certainly if you remember the Ashby plots from day 1, you'll recall that we've known what to do with gold for a while. We've known what to do with metals, some natural materials for a while. These types of materials have really only been discovered and really worked on since about 1890, but really industrial research around 1940s, 1950s, and even 1970s. Okay. And so polyethylene, probably the most common. These are your plastic grocery bags, right? These are very common in everyday life. So they're the most produced by weight. If you counted every single amount of polyethylene that's produced in the world, it's going to be, it's going to win. Or sorry, if you count all the polymers. PVC, you've seen that. It's now used in your tubing, your pipes, things like that. And it's everywhere because it's lighter, it's cheaper, right? It's heavily used, but really PVC has only been around since the 1970s. Okay. PTFE, Teflon. So you can see here, as we talk about these different polymers or these different materials, that we're changing the chemistry. So here you have 4 hydrogen atoms. Now you start replacing one of the hydrogen atoms with chlorine. You replace them, all the hydrogens, with fluorine. So I realize that these names are ridiculously long, and they might not roll off the tongue as easily. So I don't expect you to know how to name them, but I do expect you to know how to name, or what we call, the common ones. So if I say PTFE on exam, I would try to be very explicit and write out the full name. But so I don't expect you to know that it's called polytetrafluoroethylene because there's 4 tetra, fluorines on there. That's where it comes from. But I do expect you to know that PTFE, that is a repeat unit, okay? But you won't get a question like, what happens if I change one F to a BR? Now name it. That's not the point of this class, okay? So you're not going to get some question like that. But if you get a question like, if there are 500 repeat units of PTFE in PTFE versus 200, which has a higher melting point, that property I would expect you to know. Okay, polypropylene, second most produced. It's also everywhere. And then what you wear, but you might not know it, is polyethylene terephthalate, or PET. That's a little bit less common in water bottles, given that there's some BPA that's associated with the production of these plastic bottles, and hence now maybe you've experienced it, maybe you haven't, but certainly now there's a lot of stickers that say, you know, no BPAs, because there was a huge concern that PET products has, you know, quite toxic BPA chemicals that are residuals once you have it as a consumer. But it's still pretty prevalent. I mean, any PET is a type of polyester, so when you have polyester blends, this is what you're wearing. Okay. Polycarbonate, you can also find that in like battery, well, maybe older battery like lithium-ion coin cells, things like that, but still prevalent. And why do we talk about these things? We talk about them because they're commonly found everywhere. Obviously, this is just the tip of the iceberg, right? But we're going to confine our discussion to the most common polymers and the distinctions between them. Polystyrene, you all love this. We have a really difficult time recycling polystyrene. Typically in recycling, you are breaking down your polymer chains, and so it's not as useful, right? Because what I just said, right? The chain length dictates the melting point. So when you change the chain length, you're now changing the material's properties. So what you desired before, what you were engineering it before, no longer holds. So you can use it for a different engineering purpose, sure. But that's not really recycling, right? You're not reusing it for the same purpose. You have to find another purpose for it, which is not the end of the world, but it's now different materials properties engineering. Okay, so recycling is difficult for some of these polymers for these reasons. So polystyrene, you can add colorants to them. You get your green packing peanuts, orange packing peanuts. That's just a polystyrene foam, right? So when you have like your saran wrap, let's say your plastic wrap that you put on food containers or your, you know, leftover dinner and whatever, and you stick that in the fridge, why is that transparent, but your polystyrene foam, which is also 100% amorphous, is not transparent? When you go to a food truck or you do takeout, it used to be that polystyrene or styrofoam was quite prevalent before, you know, we decided to be a little bit smarter and use, you know, other recycled materials like paper or whatever, right? It's not transparent, but the plastic wrap that is on top, let's say, you know, that you take out of your kitchen cabinet, that is transparent, but they're both 100% amorphous. Any guess? Yeah. Does it have to do with the purity or impurity? Well, I guess it doesn't matter. Okay, so the answer with a question was, does it have to do with the crystallization or impurities that are in the material? It has to do with the fact that it's a foam. So if you had 100% amorphous polymers, it should be transparent. But in polystyrene foams, you also have air pockets that are introduced. So you no longer, so even though it's 100% amorphous, you've introduced different densities of air pockets, let's say in your styrofoam container versus in your plastic wrap. Yes. Now, can you get 100? So if you can get 100% amorphous polymer, can you get 100% crystalline polymer? thoughts? Guesses? What happens when something crystallizes? I'll help you with that. You don't think so? Yeah, so that is correct. Well, I won't say whether, you think so is a correct thing, because you have free will. You can think whatever you like. But to answer the question specifically, can you get 100% crystallinity? No, it is extremely difficult. You can see even the linear branch polymers, right? They're wiggly. They're flopping around because of the carbon-carbon backbone. And so if they're wobbling around like that, imagine trying to pack everything into a crystalline state where it's periodic, it's ordered. We talk about periodicity with crystal structures, right? You are packing every single one of those atoms into a specific crystallographic site, and you're telling everything to be symmetric and periodic. That is extremely difficult to do with polymers, even linear polymers, right? If you have all these branch, cross-links, network, what have you, they're already flopping around. I mean, good luck with that. But the linear, you think you have a chance? You actually don't, because it's extremely difficult to do so. Can you get nearly 100% crystalline polymers? Absolutely you can, but to get absolutely 100% crystalline, that's difficult and actually impossible. So we've deviated from our groups, PMMA, polymethyl methacrylate, Bakelite. This is a little dated in the sense that Bakelite was really popular in the 50s, 60s. People had this like everywhere. Things are like everything that you touch, was going to be Bakelite. It would be combined with some resin. You could make furniture. You can make phones. You can make whatever, vases, you name it, figurines, whatever it is. That was really prevalent in almost every household. We've obviously, have come away from that, and now there's greater diversity in the number of polymers that you have. But I want to introduce it given, the historic nature of Bakelite. Okay, and then nylon. So really, the chemical name for nylon is this long thing, but all it means is that it's a copolymer made up of 2 6-carbon backbones. So sometimes it's drawn like this, and it's equivalent. These two are equivalent, right? One is just to denote how carbon alternate in its bonding, and here it's just like, the written form. But basically, you have 6 carbon as seen here. So you have 6 carbons for one mer, and then 6 carbon, 1, 4, and 1. So that's 6. Let me erase so that it's a little bit more clear, because I'm writing over the text, but it's in your lecture slides. So anyway, nylon, also very common. Okay. So now that you're extremely enticed by the diversity of polymers, let's talk about some quantitative stuff. Yeah? Yes. It is a covalent carbon-carbon bond. So thank you for that. So in your book, what you'll see is something that looks like this. So thank you for the clarification question. So this is really, we have that incident again where the pen magically goes away. So one moment, everybody. Or I'll do that thing where I jiggle and then the USB. With all the advancements in material science, plastic to metal is not our strong suit. So there's a commercial opportunity for you right there, all the engineers in a room. So, okay, let's see. Sometimes that does the trick. I don't want to hold us. Okay, that did the trick. I don't want to hold us up too much. But to answer your question, yes. So this hexagon with the ring in it is really to denote something that looks like this. And then, but it's also equivalent to, that's an equal sign. That's not a double bond. Okay, I can see how that's confusing. Sometimes it looks like this. So it alternates, right? And when it alternates like this, if it's energetically equivalent and the double bond doesn't care, we draw it like this. Okay? And then that's connected when it shows you like this. Let me draw it over here. So one could draw it like this. Okay, that's one part. Is that clear? And then equivalently, this is CH2, so you could draw something like this. Okay, so on and so forth. So I've just redrawn this molecule, but very explicitly. Those are all covalent bonds. That makes sense? Okay. So more terminology. If you have one repeat unit, which is here, so you take this mer and you repeat it again here, and you repeat it again here, and presumably so on and so forth. We call this a Homo Polymer. That means all the mers are the same. Okay? All the repeat units are the same. Now, if they're not, then we call that a copolymer. And you can have two. Really, the cases that we'll deal with here is really just two different types of mers bonded together and polymerized. Obviously, you can get much more complex. We're going to stay away from that just to focus on the concepts itself and not really on the chemistry. Okay, but copolymers, you really want to bring two different types of mers together, either to have some sort of targeted functionality or some sort of other, chemistry where you want to make one part like more hydrophobic, the other hydrophilic. Whatever it is that you're targeting for, you would consult a polymer chemist and say, okay, here's what I want in terms of properties. Let's design a copolymer together, and this is what you would work on. Okay, but that's the definition. If all your mers, if all your repeat units are the same, it's a Homo polymer. If they're not the same, it's a copolymer. Okay. So now let's get to molecular weight. So we'll talk about degree of polymerization, number average molecular weight, and weight average molecular weight. Because, as you've noticed, even within a polymer, not all the chains are the same, right? There's always a distribution because of the synthetic conditions, right? It's not always so easy to say if I want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I want 10 repeat units, that you can reliably make 10 repeat units every single time in a batch, right? You're going to have some weight distribution. You're going to have some chains that are 11. You're going to have some chains that are 20. You're going to have some chains, maybe the reaction went wild, you have 100. So what is the average of that? So we talk about in two ways. We talk about the number average. So we're just counting. Okay, I have 10 chains that are length 10. I have 20 chains that are length 1. Or, okay, that's a terrible example, of length 3 or whatever, right? 3 repeat units. That's the number average. The weight average is you're talking about the weight itself, right? Not just how many of those chains there are. You're talking about, okay, what's the weighted average of a chain that has 50,000 grams per mole versus 40,000 grams per mole, okay? So that's why the weight average molecular weight will always win out in terms of being a larger value than the number average. The number average treats all the chains the same. You're just counting how many of each type there is. The weight average, you're focusing on the weight itself. You're saying, I'm going to weigh the 80,000 grams per mole by 80,000 grams per mole, and that's weighted more than something that is 10,000 grams per mole, okay? So your weight average will always win out because you're giving more weight to the heavier molecular weight chains, the longer chains, okay? So that answers our top hat question. Now, in this practice problem, I go through all the details of how to crank out these numbers. The main difference between what's in your book and the plot that I use, or the plot that I made, is the x-axis. So here you see the molecular weight. You see that it starts at 5. Well, it's actually times 10 to the 3. So it's actually 5,000. And it ends at 10,000. Okay? So what would be the average between 5,000 and 10,000? Just an exact average. 7.5 or 7,500. Okay? So that would be the middle. So in my plot, I used 7,500, or I used the exact average and plotted that. The representation here is it gives you a starting number and an end number, and you take the average of that. Same methodology, just two ways of representing the numbers. Okay? Hopefully that's clear when you watch it. Okay. So let's see. With the remaining time, I think I could go over that problem. Let me just talk about, for a few minutes before we do the practice problem, let's talk about the length itself. There can be confusion when we're talking about the length of a chain. When we were talking about some simple example like this, let's say this is a linear chain with, MERS. Are you talking about this length, which is the extended length from end to end? But sometimes when this length, let's say the same length coils up like this. Do you talk about this length? Do you talk about end to end? Do you talk about what happens when you unravel, in which case you talk about the total or the extended length? That can be confusing in the community or when you just talk every day. So we have a definition, and that definition is when we're talking about end to end like this, in your book they call it R. There's also another representation, it's called L bar, like this, as you can see here. But either way, that is just the number of bonds in your chain, number of carbon-carbon bonds in your chain times L. Little l being, so if, for example, carbon-carbon bond is 0.154 nanometers. So if there are 1,000 repeat units, there are 2,000 bonds, because what happens is when you have a monomer like this, let's say polyethylene, because we like this example so much, when you take a monomer like this and then you make it into a mer, what happens is you take away this one of the double bonds and you make it into another single bond, okay? So you get 2 bonds out of every repeat unit. I'm going to repeat it. You get 2 bonds out of every repeat unit, out of every mer. So if you have 1,000 mers, you have 2,000 bonds, okay? And then this bond continues on. Now, what happens to this bond? Well, once again, through symmetry, this bond is technically also this bond, just repeated in either direction, okay? So you get 2 bonds for every repeat unit. And some people refer to it as M. Your book refers it to as capital N. If you go on and work with some polymer person, it could be either, okay? Or you can just spell it out and you say how many bonds do you have, right? So that's how we calculate chain to chain. It's just L times, little l times square root of the number of bonds that you have. Yes, question? The little l is the carbon-carbon distance. So that is this guy right here. Let me highlight it in blue to be clear, because I know some of you are taking notes, and when you look up, it's like, what did she highlight? Yeah, it's the one in blue. This is 0.154 nanometers. Yes, it shortens a little bit, but in these mers, you only have carbon-carbon single bond. You have saturated polymer. Okay. But yes, to answer your question, does the bond length change when you go from single bond to double bond? Yes, your double bond length is shorter than your single bond length. Okay, so I go through this in great detail. I know I just went through it super fast, but in the same playlist, I go through this in great detail so you can review it. One of the reasons why I make the tutorial videos is because we don't always have time to highlight all of the important points. And also, it's not the most conducive environment because you're taking notes and you're listening to me and you're looking at your other notes, So please take a look at the tutorial videos. I actually slow down. My cadence actually slowed down. So that way I go through all the computation and all of these points, okay? So if you feel like, you missed something, 1, it's in your book, but also 2, if it's not in your book, if I've added something, the lectures are recorded and they're posted. And of course, I select some of these problems to do in greater detail, and I post it all in the playlist, okay? And of course, you can always contact us if you have additional questions, okay? So, all right. So let's see. So we've defined degree of polymerization. So if you know the molecular weight of your polymer and you know the weight of 1 mer, that ratio gives you the number of mer units. That's your degree of polymerization. So if you have a higher degree of polymerization, that means you have a longer chain. You have more repeat units, right? And that also increases the molecular weight of your polymer. Okay, so let's see. Your top hat has some practice problems. In the interest of time, let me highlight one of the more involved computational problems to work on that. If I'm allowed to by this computer. Okay. I know I'm speeding through this. This is actually all done in the lecture notes, so I just want to get to, I want to get to crystallization and also the practice problem. So we might have to pick up here in a little bit. Let's see. Yeah, so I want to get to this practice problem, at least to strategize together, even if we don't work out all the numbers together, because this is actually outlined and done in detail in the video. Okay, so when you have to calculate the number average molecular weight, the weight average molecular weight, and the degree of polymerization, you're giving this data this plot like this, you can actually tabulate all the data yourself. You don't need to be given a data table. So here it says that, here's the fraction of polymer chain as a function of the molecular weight. So what this is telling you is in your polymer, you have different chain lengths, and thus you have different molecular weights within these chains. Well, how much of your polymer, what is the distribution like in your polymer, right? So here it says, so that's noted as xi. So when I say percent, I'm already converting 0.25 to 2.5%. So this is saying that 2.5% of your polymer, whatever like somebody hands to you, like a goop of something, 2.5% of that has this molecular weight, and that's 15,000 grams per mole, or 15 kilograms per mole, okay? So that's what they're saying. And so in order to calculate the number average molecular weight, the definition of that, this is the number average molecular weight. That's equal to xi times mi, and the summation of all of those weighted fractions. So let's read off the plot here. So here, 0.1, or 10% of your polymer has 25,000 grams per mole, okay? And then I can go on and tabulate. So here, 0.15 is 35,000 grams per mole. And I can do this and tabulate all the way up to 85,000 grams per mole, okay? So I can read off all of these values, okay? Okay, so then I can calculate xi times mi, and I can tabulate all of these values by just doing multiplication. And then in order to get the weight average molecular weight, I need to calculate or tabulate what W sub I is, or the weight average, the weight fraction. The weight fraction is just given by, so you take this value, xi times mi, divided by this shouldn't be, oops, wrong notation. I jumped ahead. Sorry, everybody. Is xi times mi divided by the number average molecular weight. So you can tabulate that. And then your weight average molecular weight is just summation of Wi times